Okay, so here we'll do part 2 of the slides. And we'll focus here on the plotting and the goodness of fit and statistical significance using the regression output to really understand what's going on. And we will be using the Anscombe dataset, which is a very, very simple dataset, trying to understand education spending per capita among the US states. So we're here, let's plot what we estimated. Remember, we estimated a regression model called reg. Let me just go back. There's the reg, and that's the reg. If you type reg, it will just give you the basic function output, which is the model, the most important part of the model. But you should always try to use summary to get more information. And we'll, at this point, we'll understand each and everything here, right? So call, we've already mentioned that. This is the structure of the call, data, and then you give it the data set that you have, and the data set should be long. And then the formula should be of this form, the y as a function of, which is this, this is a tilde. Now I remember it's a tilde. Tilde income, and this is a simple OLS. There's only one regressor, income, but you could add more things here. Okay, it could be, here I'm just gonna type stuff like plus urban plus and so on. So there are other variables in the data set, but now we're highlighting simple OLS with only one variable. Now let's do ggplot2. You should load it, and then here let's go through each line. ggplot data is the data that the data set, right? And then you will plot the points of y x income versus y education, and then we will geom line, which is income, the x-axis, the x variable, and y, which is predicted education. So let's go back to that. So here's our data. We don't have predicted education yet. That's the one thing we haven't done. And we have learned, however, that predict will allow you to predict using the regression model. So another way of also writing it, which is the same. Let me just copy this. Because we're not using new data, this could also be fitted. Okay, so these are two equivalent things. Use predict. Predict is different from fitted if you have new data, right? So let's go to predict. And then, again, this is something you should keep doing, right? If you have an issue with the function, you should just use question mark the name of the function. Predict is a generic function for predictions. Predict object ... Additional arguments affecting the predictions produced. So there's a new data here because it's predict LM. Object, new data. So the new data is an optional data frame in which to look for variables in which to predict. If omitted, the fitted values are used. So when you have an LM object, like reg, it will use predict.lm, and the new data will default to fitted to the actual data in the data set, and will produce not a predicted, as in new data, predicted from new data, but fitted. So it's predictions from the existing data. Okay, so let's do that. And now our data will have a new column, and the new column is called predict educ, which is our prediction for each state, what their education spending per capita is. Cool, right? And you can see that with the head data as well. Now we've loaded ggplot2, and then we are now going to plot actual education spending to predicted education spending in the same plot. And the line, which is the predicted education spending, will be colored red, which is this, which is also here in our PowerPoint. So we've got these different points. These points are the actual data, and the red line is your predicted relationship between education and income. Now, again, let's just go back to the point of all of this. We are interested in the population level parameters, meaning the relationship at the population level of education and income. So you might think of a population level as like the data generating process, which generates all of the data on education spending by states over time, and income, right? So you've got all of this information on there's this data generating process that generates education spending per capita and income spending and so on, and you're trying to relate these two according to that population level relationship. Okay, and then you're postulating that there's in fact a stable population level relationship, and this line here is based on a sample from that data generating process, which gives you a specific line or a specific slope relating education and income. And as usual, if you choose a different year, say this is 1970, you choose 1971, then you'll get slightly different numbers and then a different slope. And then 72, slightly different numbers for both and a different slope. But then if you look at all of those different slopes and you're averaging all of those, then if this were blue, BLUE, then all of those different draws from the population data generating process will lead you essentially to the same, on average, will lead you to the same relationship. Okay, so this is just me recapping the earlier discussion. All right, so anyway, this is our slope from this particular sample. Now, this is again what OLS does, and I hope that this was introduced to you before. So U is the measured error terms, right? The measured error terms, squared error terms, which is just the difference between the y-hats and the y's. The y's being the actual data, and then the y-hats being the expected y conditional on x, which is based on the coefficients that you will try to determine based on this minimization problem. You're minimizing this sum of squared residuals, and then you can basically, instead of y hat, you can insert this, and then this will allow you to, if you were to take derivatives with respect to alpha hat and then b hat, it will allow you to calculate what the alpha hat and the b hat is, the optimal alpha hat and the b hat is, because those are the two things you don't know, right? You don't know alpha hat and b hat, and you're choosing those to minimize the sum of the squared error terms here, right? So in this plot, you've got the y hats, which are the reds. Those are the quote-unquote fitted or the predicted. And then the actual data is the black. What I've done here is to draw vertical lines, which are the residuals, the values of the residuals, right? So there are residuals all over here, which are the difference between the black, the actual, and the red, which is the predicted. Okay, so residuals will play an important role in our analysis, and it's important for us to really be comfortable in assessing and looking at the distribution of the residual values. So the first thing we're doing here is we're plotting the density, and I think I've got that here. So first, the command is residuals. So if earlier the command was predict, this command is residuals. And here we're creating a new column called resid, which are the residuals of the regression model. So again, let's look at that. So now you've got education, predict, and you've got the residuals. And the residuals will be essentially the difference between the predicted and the actual. So here, 189 minus 174 is roughly 14.9. 169 minus 198 is going to be negative 29, and so on and so forth. Yeah. Now you've got ggplot income, G on point, segment. Oh, this is the difference, highlighting the gap, the lines between the black and the red. The red being the predicted or the fitted, and the black being the actual. Next, we will look at the histogram. These are the histogram. This is the histogram of the residuals, right? So what would we like to see here? We'd like to see basically a normal looking curve, that is around 0. And for it to be symmetric on both sides. It's almost like that, except for two things, except for one thing, really. We have this one, which is this big outlier here. So the question is, what is this? This is the one that makes it, which gives us a problem. Because a problem in the sense that it doesn't look like a traditional residual distribution, which is you're interested in a residual distribution, which has a mean zero and it's distributed evenly from left to right. So this is an interesting thing that we want to investigate later on. And in fact, here in the PowerPoint, we'll realize that it's Alaska. Alaska is a big positive residual. And a positive residual means its actual spending is way higher than its income level would say, relative to everyone else. It's spending a lot of on education. So that's what this means. And a negative residual would be the opposite. You're spending less than what the average state is doing. And then here in this picture here, you can see that Alaska is this big positive residual here. Right? Spending a lot more on education than its income level would say. Okay, so this extreme value is changing the slope of the regression line. So that's called leverage, which we will talk about in a later installment of this video, but it will be part of this series of slides. Okay, so next we'll talk about prediction. So let's say that you have a new data point for xi. Can we predict y? That's y hat. And what's the prediction error? So obviously, yes, y hat is quite easy because you just replace x with this new x, and then y hat is basically alpha hat plus b hat plus the new x. So that's not really the issue. What's the issue is the prediction error. So we can show that the error bands are t-distributed for a large n. So it's basically this, and this being the standard error of your residuals. Okay, and you use the code predict reg interval prediction, which is a prediction interval. Now the prediction interval is the range of values where in 95% of the time the y hat I based on the new data point on xi is expected to fall in. So a prediction interval is the interval for a single prediction. Okay. And we'll do it here. We'll skip all of this first. And we'll jump to the prediction interval down here. So data predict reg interval prediction. So this is data pred. The fit is this. The lower part is 102 and the upper part is 245. So these are huge 95% confidence intervals. You are excluding 0, thank God, but it's still quite large. We're talking about 200, well, not really 200, well, 150 US dollars per person on average, which is the gap between the small number and the big number. So, and that gap is essentially going to be constant. That large, depending between for whatever the new observation will be. Okay, so anyway, we will plot all of this by giving data the lower value and the upper value, and now we will plot that and incorporate the low value by plotting a geom line for the low value, giving it a line type 2, which is a dashed line, and then the upper value, which is also a line type 2. And that's what we've got here. So this is the prediction value. If there is another prediction within the range here, it's going to, for example, if you have a new data and that x happens to be 2,500, that single data could lie here or anywhere within this range. Okay, but that's for a single data, right? That's a prediction error. Now, a confidence interval is something else entirely. So the confidence interval is the range of values we expect the average y given x to fall in. because we're estimating the average y, not a single value. The confidence interval is going to be narrower than the prediction interval because the OLS is really designed to really give you stronger statements on the average y conditional on x. So the blue bands here are the CI, which is the confidence interval on the prediction of expected y, right? So in other words, if your income is this in this area, and if you had a lot of different draws on X, then you'd expect the average of all of those draws will be somewhere here in the middle. Individually, it can be anywhere, blue, 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 like that. But if you average over all of these, it's gonna lie in here 95% of the time. So let's do that. The confidence interval of the mean. Doing the same thing, creating a new column for lower and the upper edges of the distribution. And then here, you were drawing the line itself. By the way, for the ggplot nerds out there, look at the theme BW. It changes the look of the plot. And I personally like theme BW better than the standard default one. Okay, so let's talk about goodness of fit. In your class, you'll probably learn about R-squared. So that's available in the output. Okay, so how would you get that? So reg is here, but reg dollar here. Oh, hold on. The R-squared is here. And there is an adjusted R-squared based on the number of coefficients here. So the more coefficients you have, that will create more of a difference between this multiple R-squared and the adjusted R-squared. Boom, boom. Okay. The R-squared looks at the proportion of variation explained by the regression. So this is R-squared. So this is y hat minus y squared over yi, which is the data, minus the y bar, right? So the model is in the numerator, and the data, essentially, the spread around the mean, is in the denominator. So if y is moving a lot, your y hat should explain that as well. Should be as variable as your actual data. The command coefs will get the coefficients. So that's R-squared. Okay. So usually our concern is with the coefficients, and the confint command gets the confidence interval. And here we have the betas are distributed according to t-distribution, according to this. So let's use the confint command. And here we have the 95% confidence interval for income and for the intercept, which we already discussed earlier. And that confidence interval is basically around here, right? Where B1 happens to be your null hypothesis. Okay, so the null hypothesis happens to be 0 in this case. So this is a confidence interval around beta, and if it includes 0, then it is not significant. So the value of the t-stat at the given degrees of freedom at the 95% level can be found in R using a dt command and can be approximated by the standard normal. And this is 1.96. Right? So it's approximated by standard normal because usually there's a difference between dt and the standard normal. But as n goes up, typically n greater than 30, the t-distribution and the standard normal is essentially the same thing. So let's look at the coefficients. Here's the summary reg coefficients. Let's try that. This gives you that table. Okay, the estimates, the standard errors, the t-values, and the p-values. These are p-values. Okay, so let's think about it. So we use these information to test for the statistical significance of the estimate. Okay. Remember again that the null hypothesis is where the coefficients or the estimates are equal to 0. So the key question is whether these estimates are significantly different from 0, or in fact interpretable as different from 0, based on the error that we found. Now, we can do that by the t-value, primarily. And the t-value is based on this thing, right? Where bi minus b1 over se. And that's the t, right? So remember, boom here. So if you move this b1 to the left, so that's bi minus b1, and then you divide it by the se, and that gives you the t-stat, right? Whatever it will give, the t-stat is basically something that you will get by bi minus whatever your null is divided by the standard error of b. And that's exactly what you get here. So b10 is basically 0, normalized to 0, and that's the standard null hypothesis. You're comparing it to 0. You're comparing b hat to 0. And the example above, the income coefficient is 0.055 divided by the standard error 0.0088, which happens to be 6.28, which is the t-value here. Okay. Now we've known that the critical is 1.96, and every time that the t-value is greater or approximately equal to 1.96, and that means you are statistically significant at the 5% level at least. Okay, so that's the relevance of the t-value. Now I invite you to look at this 0.06. Clearly that is less than 1.96, so it is not significant at the 95% level. So that means you cannot statistically distinguish 17 from 0. It could be 0. Okay, so these are all the same things. The confidence interval here, 0 is inside the confidence interval. And here a p-value of 0.6, which is less than 1.96, which means you cannot exclude 0 from a 95% confidence interval. These are all related. The critical value, the test value of t is greater than the critical value. Those are all related concepts, essentially synonymous to each other. Okay, so given, the intercept, alpha hat, has what t-value? We've already discussed that, and compare it to the critical value. Clearly it's less. So what's the conclusion? Is it statistically different from 0 or not? Right? So that's something we should determine. Now the same information can be gleaned from the p-value. So instead of looking at the t, you can look at the p-value, which are these things, right? So let's start with this p-value here. For income, the p-value is 8.76, etc. Times e to the negative 0.08. E is not really exponent. This is really more of the 10th power. So what this is you move the decimal point 8 spaces to the left. So it's really, really small, right? So the p-value is really, really small, which means you move the decimal point 8 spaces to the left. You compare it to your type 1 error, which again is 5%. And 5% is 0.05. So 0.000008, 8 zeros, 7 zeros, and 8 is the 8th number, is definitely less than 5%. So the area under the curve is small that you're predicting a type 1 error, because it's that unlikely to get this number if the true value is in fact 0. So again, I'm going back to the original discussion, right? So in what sense can you reject an estimate, right? You can reject an estimate if what you get is sufficiently so far away from the mean such that, sure, it's still possible, meaning to get this, it will be this %, right? Under the null of 0. So in which case, you're fine, because you already said that if it's less than 5%, you're okay. And this is definitely less than 5%. So you're making a mistake less than 5% or approximately 0.0008% of the time. And you're accepting that probability of a mistake. So later on, we will use simulation to check what happens when we break the linear model assumptions for blue, right? So remember, most of our assumptions are population level assumptions, especially the exogeneity one. So that's pretty important. And when it comes to exogeneity, you'll need something more advanced machinery, but it involves both econometric theory and economic theory put together. So it's a little bit more advanced, and that's for another course, right? But here, what we will do is we will basically assume a certain kind of population DGB. And then when the population is like this, and then you attempt to use OLS, what will happen? So that's what simulation is so useful for students of econometrics, because you can posit whatever data generating process at the population level, and then you can pretend you're extracting samples from that data generating process, and basically OLS estimates thousands of times, and then you get the average of those thousands of estimates, and then it will tell you if you're unbiased or biased, or consistent or not. We will learn about consistency later on. But for the usual cases with real data, we would like to use regression diagnostics. I will focus on a cross-section case here and defer to time series later on. With regression diagnostics, you cannot really assess exogeneity per se, but you can assess how you can assess heterogeneity, number one, and two, model selection, which is basically, do you think there's something in the data that's still needed, some additional variables that you might want to put into the model, and the regression diagnostics will help you with that. It can also help you with the linearity assumption. So remember before, we were saying that the OLS is a linear approximator for the population, but it's robust to transformations. So it's possible to transform Y and X such that when you transform them, they're still linearly related, but then when you plot them, Y and X, they're not linearly related. Well, it will be clearer later on. I'm thinking actually to add some more slides when it comes to linearity or non-linearity, but we'll get to that maybe in 2 weeks. Okay, so but that's basically the use of the regression diagnostics, right? And we will check those regression diagnostics really soon. The key assumptions, you can't really use regression diagnostics like exogeneity, like we just said. But for everything else, heterogeneity, linearity, then you can definitely use regression diagnostics. Okay. So it's important for you to plot and generate the residuals every time you do a regression. Okay. I guess the most practical concept is the concept of leverage. So that's why I will spend a lot of time in the next video just talking about leverage. So an individual observation has leverage when it's an outlier on the y or x-axis, which then would have an effect on the size of the coefficient. So not all outliers have leverage. It depends on whether it's close to x bar or not, right? The closer it is to x bar, the less leverage it has. So we will talk about leverage in the next video. All right, thank you so much.